Chapter 7 is where we start the statistical inference part of the course, and we'll begin with sampling and sampling distributions. Now, Chapter 7 covers selecting a sample. It also deals a little bit with point estimation. We'll actually get more into the concept of estimation itself when we get into Chapter 8, when we start doing confidence interval estimates. But the big deal in Chapter 7 is the introduction to sampling distributions. Primarily, we're going to be dealing with the sampling distribution of the mean. That's what the symbol X bar is. We're going to cover a little bit about the sampling distribution of the proportion, the P with the dash across the top of it. We'll call that P bar. And then there are other different ways that you can take samples. We'll just kind of mention a few of those. When we don't have all the members of the population, when it's unwieldy or it's not feasible to look at all the members of the population, what we do is we just select a random sample, and then we can use those statistics. They're called point estimators that we get from the sample, and use them to estimate things about population parameters. We'll get into the estimation of population parameters when we get into Chapter 8, but the idea is that there's a relationship between those population parameters and the sample statistics. And if you do your sampling correctly, you can do a pretty good job of estimating those population parameters. Now, the example that's being used to show the calculations is St. Andrews College. They received 900 applications. Part of the information that was on the application was the student's SAT score. That's a quantitative measure. Another part of it was whether or not the individual wanted to live on campus, the on-campus housing. That was qualitative or categorical. Now, they have all these applications in, but they don't have the ability to just instantly come up with the numbers. So they just have a few hours, and they would like to, make a statement as to what the average SAT score was and how many of the applicants want to live on campus for the entire population. So what they're going to do is they're going to look at a sample. Now, the theory of sampling distributions, we're trying to show the relationships between the population parameters and the point estimates. The sample mean is a point estimate of the population mean. Now, just right before the meeting, they don't know that the population mean is 1,697. But they take their sample of 30 and they can calculate the sample value as 1684, which is pretty close. They don't know right before the meeting that the standard deviation is 87.4, but they can figure out what it is for the sample. Same thing for the qualitative data, for the categorical data. They don't know that the population proportion of the people that want campus housing, we use the symbol P for that one. They don't know that that's 0.72, but we know what the sample value is. But in order to show you the theory of sampling distributions, you assume that you know the population values, and then you can show what the relationship is relative to the sample values. And then when we get into Chapter 8, we're going to show you how to turn this kind of inside out, how you can take the sample value and use it to estimate the population value. Now, most of the time in Chapter 7, we're going to be dealing with the sampling distribution of the mean. Now, no matter how you sample, whether you sample with replacement, without replacement, order matters, order doesn't matter, it's always going to be true that the expected value of the sample mean is going to be the population mean. And when you have that relationship between a statistic and a parameter, the statistic is said to be an unbiased estimator of that population parameter. And in statistics, it's desirable to have that property. You want to have that unbiased nature. But the average of all the sample averages is always going to be the population average. But when you look at the variance of the sample mean, that's going to be different depending upon how you sample. Now, the formulas that we're going to be using in this chapter they assume the common type of sampling is that you sample without replacement and order doesn't make any difference. If you change the way that you sample, you can change the formula for the variance of the sample mean. But the mean of all the sample means is the expected value of all the sample means, and that's the population mean. Now, if your underlying population is normally distributed, then the sampling distribution of the sample mean is always going to be normally distributed. It doesn't make any difference whatsoever what the sample size is. But if you have a big enough sample, you can treat the distribution of the sample mean as though it's normal. And the size that's ordinarily recommended to check for is 30. If the sample size is at least 30, you can treat the sample mean, regardless of what the distribution of the population is, as being approximately normal. Now, in certain, I guess you could call them pathological cases, when you have really, really skewed data, or you've got some outliers that are just way far away from the mean, you may need a sample size of at least 50 before you want to consider it to be normal. Now, the central limit theorem is one of the most important results in inferential statistics. The mean is the statistic that gets analyzed most of the time. So it's nice to know whether or not it's normally distributed. Well, you can approximate it with a normal distribution if your sample size is large enough. And the rule of thumb is 30. If the sample size is at least 30, then we're going to go ahead and treat the sample mean as though it's normally distributed. Now, anything that's normal, we can convert it to the standard normal. All we have to do is subtract the mean and divide by the standard deviation. Well, it turns out that the mean of the sample means is always going to be the population mean. But the standard deviation of the sample means, the formula for that is going to be a little different depending upon how you sample. Now, these are some of the symbols that we're going to be using. We're going to use the symbol sigma with the subscript of x bar to represent the standard deviation of x bar. Likewise, you could use the symbol mu with the subscript of x bar to represent the mean of x bar, the expected value of x bar. Another name for the standard deviation of x bar, it's called the standard error of the mean. But the symbol sigma by itself is the standard deviation of the population. Lowercase n's the sample size, and uppercase n's the population size. Now, we're not going to go through the derivation of these formulas, but if you have a finite population, if you know what the value of capital N is, then there's a correction factor that you can use to figure out what the value of the standard deviation of the sample mean is. And you take the correction factor, take the square root of it, and you multiply it times sigma over the square root of n. But that correction factor is being used for the fact that you're sampling without replacement from a finite population. And it's called the finite population correction factor. Now, that factor is going to be really close to 1 when you meet something that's called the 5% rule. If the sample size is less than or equal to 5% of the population size, then there's really no need to correct for it. You can use the formula that's on the right for the infinite population. You can just use the standard deviation of the sample mean as being sigma divided by the square root of n. Sometimes it's referred to as the standard error of the mean instead of the standard deviation of the mean. Now, this illustration shows for the St. Andrews College, we do have a finite population. We have a population of 900, but the sample size is only 30. If you take 5% of 900, you're going to get 45. 30 is less than or equal to 45. So in this problem, we do not need the correction factor. All we have to do to get the standard deviation of x bar is to take sigma and divide it by the square root of n. So sigma in this problem was 87.4. The sample size was 30, so we divided by the square root of 30. And that's approximately 15.96. 15.96 is the standard deviation of the sample mean. 15.96 is the standard error of the mean. The mean of all the sample means, the expected value of x bar, is the population mean, and that was 1697. So when you look at the possible x bar values, the mean of all the x bar values is going to be in the middle. The 1697 is in the middle. We have a sample size of at least 30, so by the central limit theorem, we can assume that the distribution of the sample mean is approximately normal. So we can put that number in the middle. So we know what the mean is for the sample mean. We know what the standard deviation is for the sample mean. So we can use those two pieces of information and calculate z-values. Now once you know the z-value, you can look up the probability in the table. Now St. Andrews College, we want to figure out what the probability is that a simple random sample of 30 applicants will give us an estimate of the population mean SAT score within plus or minus 10 points of the actual mean. So we're assuming in this case that we know what the mean is, and we want to see, well, what's the relationship between the sample values and that population mean? So we're assuming that the mean is 1697. If we go 10 units below that, we're going to be at 1687. If we go 10 units above that, we're going to be at 1707. So the question is, if the mean is 1697, what is the probability that the sample mean, we just take a random sample of 30, what is the probability that the mean in that sample is going to be between 1687 and 1707? Now, the essential elements that you want to see from this problem is that you want to find a probability about the sample mean. Now we're going to need to know whether or not the sample mean is normal. And if it turns out that it's normal, we're going to need to know what formula to use to give us the value for z. And what I've done is I've fixed up a little device that I'm hoping is going to help you to do that. This is the flowchart. We have a problem to where we're trying to figure out the probability about a sample mean. So you follow the path from the left with respect to the mean. If we were doing a problem on a proportion, then we would take that downward path. The next question is whether or not you know sigma. Sigma is the population standard deviation. If you know that value, if we have a normal population, well, we can just go ahead and use the z. But even if we don't have a normal population, or we may not know whether or not it's normal, if we have a big enough sample size, if n is at least 30, then we can still use the z. Now I've gone ahead and put in the formulas in this flowchart for confidence interval estimates. You're going to ask the same questions to figure out what the formula is to do a confidence interval estimate. And so I've already got that formula down there, but we're not going to be using that until we get to Chapter 8. But the elements that you need to be able to find that z-value, you need to know what the mean of the population is, you need to know what the standard deviation of the population is, and you need to know what the sample size is. The value of x bar is going to be specified in the problem. In this case, we want to find the probability that x bar is 10 units below the mean to 10 units above the mean. And we're going to be able to figure that out by using our z-table. Now again, I strongly recommend that when you're working out one of these normal probability problems, that you draw a picture of it. The mean of all the sample means is 1697. So I've put 1697 in the middle when you're looking at x bar values. Now the formula that I got from the flowchart is x bar minus mu divided by sigma over the square root of n. But another way to write it is in the form of the x minus mu over sigma. But the x is the sample mean. You take the sample mean, you subtract the mean of the sample means, and you divide by the standard deviation of the sample means. And so when we plug in the numbers, we're just going to get x bar minus the 1697 divided by 15.96. 15.96, you get that number when you take the value of the standard deviation and divide it by the square root of the sample size. Now we want to find the part that's in blue. We want to find the likelihood that the value of x bar is between 10 units below the mean and 10 units above the mean, that it's between 1687 and 1707. And all we have to do is use this formula up at the top of the curve to convert those x bar values to z values. So here are the calculations. 1687, we just plug that in for x bar, and we figure out that the z value would be a negative 0.63. Now the one on the other side, because it's the same distance, it's just 10 above instead of 10 below, we come up with a value of positive 0.63. But now that we have the z values, we can go to the table and figure out the probabilities. Now on this slide, all I've done is I've changed the scale. The axis that's down at the bottom, I've changed it from an x bar axis to a z axis. We want to find the probability that the z value is between a negative 0.63 and a positive 0.63. And we can get that information from the z table. Now we go to the z table. Now remember, the z table, if you look in Chapter 6 and you go into the videos for Chapter 6, the document's in there. It's a 2-page document, and this is on the second page. These are for the positive z values. But we have a z value of positive 0.63. So when you go down the left-hand side, you have the units and the tenths, and that's going to identify which row you're in. So the units and the tenths are 0.6. So we're going to be in the 0.6 row. Now in the hundredths position, we have a 3. Now the hundredths position gives you the column. So we go over 0.00, 0.01, 02, 0.03. And when we intersect those two, we're in the 0.6 row, we're in the 0.03 column, we get our probability value, which is 0.7357. But the probability that you get a z value that's less than 0.63 is 0.7357. Now you go to the other side of the z table, where you have the negative z values, to figure out what the probability is that you have a z value that's less than or equal to a negative 0.63. Now the way I organize this table, I put the z values on the right-hand side. But it's still the units and the tenths will show you which row it's in. And the hundredths position is going to show you the column. So we go all the way down close to the bottom to find the negative 0.6. And then we go from the right to the left. We get the negative 0.01, the negative 0.02, and the negative 0.03. And then we intersect those. And the probability value at the intersection is 0.2643. So the probability that you get a z value that's less than or equal to a negative 0.63 is 0.2643. Now if you want to find the probability that's between 2 points, ordinarily all you do is you just find the two z values, and then you look up the two probabilities and you take the difference. I'm trying to give you a kind of a static visual representation of this. When we looked up the value 0.63 on the chart up at the top to the left, from the table we got the value of 0.7357. But the part that's shaded in blue is that 0.7357. Now when we went to the other side of the z table, where we had the negative values, and we looked up the negative 0.63 down at the bottom, the value that we got from the table was 0.2643. Now you can kind of visualize that if you took the chart at the bottom and moved it up over the chart up at the top and lined them up, then the part that's in orange is going to cover up part that's in blue up there. And that illustration is on the right hand side. But what you need to do to get the part that's between a negative 0.63 and a positive 0.63 is just take off that 0.2643 from the 0.7357. Now if you have trouble seeing what's going on here, I made a little video to try to get a little bit of more movement into this, and it's in the video part in chapter 7, and I think I just called it normal video. But if you open up that little video and look at it, it may make it a little bit more clear as to what's going on here. But the point is, if you want to find the probability between two values, you've got to get the z values, and then you can look up the two probabilities and you just take the difference. Now this doesn't have anything to do with one of them being a positive z value and one of them being a negative z value. They could both be positive and you're still going to take the difference in the probabilities. They could both be negative and you're still going to take the difference in the probabilities. You cannot have a negative probability. You just subtract the smaller probability from the larger one to get the probability that you're between the 2 points. Here I'm trying to use Excel to show the probability calculation in a little bit more visual fashion. The probability that the z value is less than a 0.63 is 0.7357, and this picture illustrates that probability in the blue portion. Now what we're going to do is we're going to look at the negative 0.63 and look at where that probability is that's smaller than it is. So from the negative 0.63 back to a negative infinity, I'm going to have that probability show up in an orange color. Now you take that part away from the 7357, and what you have left is going to be the probability that's between a negative 0.63 and a positive 0.63. But you can go to the z-table on the negative side and look up the negative 0.63, and you'll find this probability, the 0.2643, and all you have to do is subtract that from the 0.7357, and you'll come up with the part that's between the negative 0.63 and the positive 0.63. But the probability that you have a z value that's between a negative 0.63 and a positive 0.63 is the 0.4714. But maybe looking at it from this perspective, it's a little bit easier to understand what you're doing. But this slide kind of summarizes it. We wanted to find the probability that the SAT score for the sample mean was between 1687 and 1707. All right. First we converted those to z values, and then we could go to the table and get the two probability values. And then all you have to do is take the difference between the two probabilities to get the solution to the original problem. The likelihood that the sample mean would be within 10 points of the population mean is 0.4714. Now the second part of the problem is a what-if situation. We have this population of 900. The mean is 1697. These are for the SAT scores. And the standard deviation is 87.4. But suppose we had taken a random sample of 100 instead of 30. That's going to make the formula different for the standard deviation of the sample mean. When we take 5% of 900, we get 45, and 100 is bigger than that. We violated what's called the 5% rule. 100 is rather large compared to the population size, so you're going to need to apply the correction factor. So the formula down at the bottom has the correction factor built into it. We still have the sigma over the square root of n, but now n is 100 instead of 30. So you take the 87.4, divide it by the square root of 100, which would be 10, and you get 8.74. But the correction factor, we're going to scale it down a little bit. You're always going to scale it down when you increase your sample size, but when you use that correction factor, you make it even smaller. But people ordinarily ignore the correction factor if they meet the 5% rule. They just don't bother with it. The number's so close to 1 that it just doesn't change the value that much. But here it's a little bit more than 94%, so it's bringing it down a little bit. You're dropping down from 8.74 down to 8.2. But we're going to use the standard deviation of the sample mean as being 8.2. The expected value of the sample mean, the population mean, is the same. But the thing that really changes is the value of the standard deviation of the sample mean, or the standard error of the mean. Now this is a visual illustration of kind of what the difference is when you look at the sampling distributions. The part in the middle is the same. There's no difference. But with a sample size of 30, the sample means spread out further from that sample value. But if you take a sample of 100, those sample means are going to be much closer to 1697 because you're using more information. You can come up with a better estimate. But you can see that the means, the sample means, are more tightly compacted against the mu, the 1697, for the 8.2 value than they are for the 15.96 value. But it's basically taking that variability measure when you go up to 100 and cutting it in half. 15.96 is pretty close to 16, 8.2 is pretty close to 8. So it's about a reduction of about 50% there. Now we're not going to go through all the details on this one, but when the sample size of 30 was used, the answer to the problem, what's the likelihood that you'll be within 10 points of the mean, was 0.4714. You do the same problem with the sample size of 100, but you have to change the value for the standard deviation of the sample mean. And the probability increases to 0.7776. But the probability almost doubles that you're going to be within 10 points. It's just that much more likely when you take that bigger sample size. Now here's a picture that shows that result when the standard error of the mean, or the standard deviation of the sample mean, when it's reduced to 8.2 because you took a sample of 100, you get a probability of 0.7776, or almost 78% chance that you'd be within 10 of the population mean. Now this concludes the part that deals with the sampling distribution of the mean. The next slide we're going to start looking at the sampling distribution of the proportion. Now this slide really illustrates the problems that we're going to be going about solving in Chapter 8. You have a population that has a value of a proportion in some category, but you don't know what it is. So you take a sample of n elements and you figure out what the sample value is. The p bar, the p with a dash across the top of it, is the sample proportion. And then you can use the relationships that you get from sampling distribution theory to estimate the value of the population proportion. But before you can come up with the formulas that allow you to do the inference part, which is what we're going to do in Chapter 8, you need to understand how it's related to it if you know what it is. If you know what that population proportion is, how is it related to that sample proportion? And then we can take that relationship and kind of turn it inside out and come up with formulas so that we can estimate the population values when we don't know them. Now just like with the sampling distribution of the mean, the expected value of the sample proportion is the population proportion. If you took every possible sample and you calculated the sample proportion for every possible sample, and you added up all those numbers and divided by the number of samples, you would get the population proportion. It's an unbiased estimator. The sample proportion is an unbiased estimator of the population proportion. In that result, it won't make any difference how you sample. Now, if you have a finite population, there's the finite population correction factor. If you have an infinite population, then you don't need that factor. So in most cases, you're going to meet the 5% rule. Your sample size is going to be small compared to your population size, so that correction factor is going to be very close to 1, and it just won't make that much difference as to whether you use it or you don't. So most of the time you'll meet the 5% rule even if you know what capital N is. If capital N is so large that you don't even know what the number is, then you just use the one on the right, the standard deviation of the sample proportion. You take the population proportion times its complement, 1 minus p, divide that by n and take the square root. The variance is just p times 1 minus p over n, and all you do is take the square root of the variance to get the standard deviation. Now, when are we allowed to assume that p bar, the sampling distribution of p bar, is close enough to normal? Well, it's a fairly simple rule of thumb. There are two parts to it. You take n times p, that's got to be at least 5, and then n times 1 minus p has to be at least 5. But you've got to check it both ways. For example, it could be that the population proportion that you think it's pretty close to 1. Let's say it's 98%. All right? Now, if you have 100 items in your sample, well, 98% of 100 is 98, and that's a lot bigger than 5. But when you look at the other side of it, and you take 2%, 1 minus 98%, 100 minus 98%, you get 2%. 2% of 100 is just 2, and that's not big enough. So you got to check it both ways. You got to make sure that n times p and n times 1 minus p, that both of them are at least 5. But if it is, you can treat it as being approximately normal and just use z-values. Now back to our St. Andrews College example, but now we're dealing with qualitative data. We have a population of 900. The population proportion was 0.72. 72% of them said that they wanted to live on campus. Now the question is, what's the probability that a simple random sample of 30 applicants would have an estimate that that sample value would be within plus or minus 5% of that 0.72? So what's the probability that p bar would be between 0.72 minus 0.05 and 0.72 plus 0.05? But we've got a problem about a proportion. Now if we meet the little rule of thumb, is n times p at least 5 and n times 1 minus p at least 5, then we can use the normal to get the answer. So when we take 30 times 0.72, we get 21.6. That's bigger than 5. But it has to work the other way. When we take 1 minus 0.72, we get 0.28, which is quite a bit smaller. When we take 30 times that, we don't get near the number. But 8.4 is still bigger than 5, so normal is going to work okay. Now in this problem, we know what the population size is. It's 900. The sample size is 30. So when I take 5% of 900, I get 45. And 30 is smaller than that, so I don't need the correction factor. When I figure out what the standard deviation is, remember when you get your z, you take the variable, you subtract the mean of that variable, you divide by the standard deviation of that variable. So to get that standard deviation of the sample proportion, the formula is just p times 1 minus p over n. We don't need the correction factor here. So that's approximately 0.082. Now the mean of all the sample proportions is always the population proportion. So what we're going to subtract when we're trying to figure out our probabilities is we subtract the mean of the sample proportions, and that's 0.72. But basically the formula that you're getting here is you take your sample value In this case, it's a proportion. That's our p-bar. We subtract the population value, and when we divide that difference by the standard error of whatever that statistic is. So in this case, that standard error is going to be 0.082. Now we want the probability that the value in the sample, that sample proportion, is within 5% of the population proportion. 0.72 is the population proportion. So 0.72 plus 5% plus 0.05 would be 0.77. So the upper point, our p-bar value is 0.77. So we subtract the mean, which is the mean of all the sample proportions is the population proportion, and then divide it by the standard error, which we just calculated in the previous slide to be 0.082. And the z-value is approximately 0.61. Now you go to the z-table, and you'll find the probability that you're less than or equal to 0.61 is 0.7291. But the z-value is 0.61. So you go down on the left-hand side to 0.6, and then the column 1 is in the hundredths position. So you go to the column for 0.01 and you intersect them and you get 0.7291. But that's the probability that you would have a value that's less than or equal to a z-value of 0.61. Now this picture shows it on the p-bar scale. We want to find the probability that p-bar is less than or equal to 0.77. And that turned out to be 0.7291. But the 0.77, that's 5% above the mean. We also have to figure out what the probability is that it's less than or equal to the value 5% below the mean. So 0.72 minus the 5% would be 0.67. So the second part of the problem is to find the probability that you're less than or equal to 0.67. Get that probability. Take the difference between the two, and then you've got the answer to the original question. So when we convert the 0.67 to a z-value, we get a negative 0.61. And then we can go to the other side of the z-table and look up the negative 0.61, get the probability that's less than or equal to that, and it's 0.2709. And then all we have to do is take the difference between the two probabilities to get the answer to the question. But you go to the z-table to look up the value of the 0.2709, but that should correspond to a z-value of negative 0.61. So the probability that the z-value is between a negative and a positive 0.61 is the difference between 0.7291 and 0.2709, which is 0.4582. So the probability that the sample proportion would be within plus or minus 5% of the population proportion is 45.82%. This slide shows a visual representation of the original problem. What was the probability that the p-bar value is between 0.67 and 0.77? That it's between plus and minus 5% of the population value. And we figure out what the two z-values are. Look up the probabilities in the table. Take the difference in the probabilities, and it turns out to be 45.82%. The process that you go through, whether it's a sampling distribution of the mean or whether it's a sampling distribution of the proportion, the process is basically the same. You just have different formulas. So you need a mechanism that determines what the formula is that you want to use. And that's the reason that I built the flowchart, was to help people to figure out the formula. The formulas that are being used in Chapter 7 are based on the assumption that simple random sampling was used. The idea is every sample is just as likely of being selected as any other sample. To come up with the probabilities, you take 1 and divide it by the number of possible samples. There are other ways to do probability samples besides simple random samples. Here they mention stratified, cluster, and systematic. But you want to have some type of probability sampling and then have the formulas that are based upon those to be able to do estimation. You really can't do a good job of this if you just get a sample that's based on convenience or something that's just based on your judgment. This concludes our coverage of sampling distributions. Most of the homework problems in this chapter deal with sampling distribution of the mean. There may be one that deals with the proportion, but you're going to need to know those formulas for the proportion and those relationships when we get into Chapter 8. Chapter 8, we're going to deal with interval estimation. We're going to do what's called confidence interval estimates. We'll have a couple of different formulas for the mean, but there's just the one formula for the proportion. So we'll talk more again later.